Hello and welcome back. In today's video, we're overclocking the AMD Radeon RX 6500 XT graphics card all the way up to 3002 MHz using the ElmorLabs EVC2SX. It's the first time that I'll be overclocking an AMD graphics card on this channel. And in fact, it's the first time that I had a serious look at AMD graphics card overclocking since I think the AMD Radeon HD 7970 all the way back in 2012. Just like with the GT 1030 video that I launched earlier on this channel, the main purpose was for me to get back into AMD discrete graphics overclocking as it had been a while. Unfortunately, it didn't really turn out as I had planned since there's a lot of limitations that I need to share with you. So let's get started. The AMD Radeon 6500 XT is one of the two discrete graphics cards equipped with the Navi 24 GPU. Navi 24 is the smallest of the RDNA 2 GPUs and is built on TSMC's 6nm process. It is in fact the very first 6nm GPU. Navi 24 is the most low-end GPU of the second generation Navi product lineup and features 16 compute units. That's significantly less than the 80 compute units featured on the Navi 21 powered RX 6900 XT. The Radeon RX 6500 XT has a rated TDP of 107 watt, a base clock of 2310 MHz, a game frequency of 2610 MHz, and a listed boost clock frequency of 2815 MHz. It also has 4 GB of GDDR6 memory. In today's video, we will cover 5 different overclocking strategies. First, increase the GPU frequency using AMD's automatic overclocking feature. Second, we manually increase the GPU and memory frequency with the AMD Adrenalin tuning toolset. Third, we try to use the undervolting tool to increase the GPU frequency further. Fourth, we use the ElmorLabs EVC2SX to work around some performance limiting issues. Lastly, we slap on a water block to get the most performance out of our GPU. But before we jump into the overclocking, let's first have a look at the benchmarks and the hardware that we'll be using in this guide. Along with the Gigabyte Radeon RX 6500 XT Eagle graphics card, in this guide we use an Intel Core i9-12900KF processor, an Asus ROG Maximus Z690 Apex motherboard, a pair of generic 16GB DDR5 Micron memory sticks, a 512GB Aorus M.2 NVMe SSD, an Antec HCP 1000W Platinum power supply, a Noctua NH-L9i 1700 Chromax Black heatsink, the ElmorLabs EasyFan controller, the ElmorLabs EVC2SX, the ElmorLabs power measurement device, an EK Pro QDC Kit P360, and a Parami Universal GPU water block. All this is mounted on top of our favorite Open Bench Table V2. The cost of the components should be around $3,318. We used Windows 11 and the following benchmark applications to measure performance and ensure system stability. The benchmark selection is similar to the one we used in SkatterBencher number 40, except for the simple ray tracing benchmark and Tomb Raider benchmark. Since RDNA 2 has ray accelerators, it makes sense to also include a ray tracing benchmark, and I included Tomb Raider to test the PCIe performance scaling. Before we start any overclocking, of course we need to check the performance at default settings. Note that this Gigabyte Radeon RX 6500 XT Eagle graphics card is not out of the box overclocked unlike some other variants on the market. So it's running at the default AMD specification. Here is the performance at stock. When running Firmark GPU stress test, the average GPU clock is 2493 MHz with 0.958 volts, and the GPU memory clock is 2234 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 60.7 degrees Celsius and 74.2 degrees Celsius. The average TGP power is 79.976 watts. When running the GPU-Z render test, The maximum GPU clock is 2870 MHz with 1.195 volts. A big talking point of the RX 6500 XT is that it's physically limited to a PCIe 4.0x4 interface. PCIe 4.0x4 offers 8 GB per second of theoretical bandwidth in each direction, and the reduction of lanes means a cost-saving opportunity due to lower design complexity and fewer components required. On the flip side, tech media argued that some customers would use this low-end graphics card in a system that does not support PCIe Gen 4. In that case, the PCIe bandwidth would downgrade to the 4 GB per second offered by PCIe 3.0x4. Tech Power Up published a detailed article on PCIe performance scaling with the RX 6500 XT graphics card, and I suggest you to check out that one for more details. Out of curiosity, we wanted to check if increasing the PCIe frequency would improve the performance. We first checked the theoretical bandwidth using the 3DMark PCIe Express feature test. Going up from Gen 3 to Gen 4 increases the bandwidth by 87%, and increasing the PCIe frequency from 100 MHz to 110 MHz increases the bandwidth by 18%. When checking two synthetic 3D benchmarks, TimeSpy Extreme and Final Fantasy XV, there's no performance difference between Gen 3 and Gen 4. However, in a real game benchmark such as Shadow of the Tomb Raider, we find a performance uplift of 18% going from Gen 3 to Gen 4, and a performance increase between 3% and 6% when increasing the PCIe frequency to 110 MHz. There's quite some issues related to running a high PCIe frequency, so for the rest of this guide, I will just stick to 100 MHz PCIe frequency. Alright, now let's jump into the overclocking. In our first overclocking strategy, we use the automatic overclocking feature available in the AMD Adrenalin software to automatically overclock our 6500 XT. AMD Software Adrenalin Edition, introduced in March 2022, is a rebranded version of the Radeon Software Adrenalin Edition and the successor of the Crimson Relive Edition software package from 2016. In short, the software includes not only the graphics card drivers, but also a bunch of valuable tools for fine-tuning your gaming experience. As this is an overclocking guide, I will skip all of the gaming features and go straight to the overclocking. Embedded in the Adrenalin software, you can find a segment dedicated to performance. That includes logging metrics and tuning knobs. As part of the tuning knobs, you have three options for automatic overclocking: undervolting the GPU, overvolting the GPU, and overclocking the VRAM. Unfortunately, we can't do all three simultaneously, so for this overclocking strategy, we just overclock the GPU. Upon opening the AMD Adrenalin driver software, go to the Performance tab, click on Tuning, under Automatic Tuning click Overclock GPU, click on Proceed, and then click OK. We reran the benchmarks and check the performance increase compared to the default operation. Since we're using an automatic overclocking function, any performance increase is essentially entirely free. We see improvements ranging from 0.66% in FurMark 1080p to 5.59% in Final Fantasy XV. When running FurMark GPU stress test, the average GPU clock is 2532 MHz with 0.958 volts, and the GPU memory clock is 2234 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 63.3 degrees Celsius and 78.1 degrees Celsius. The average TGP power is 84.748 watts. When running the GPU-Z render test, the maximum GPU clock is 2901 MHz with 1.195 volts. Now it's time to start our manual overclock. But before we get to that, let's look at AMD's GPU frequency boost technology. Over the past couple of months, I've done quite a couple of videos where I have a closer look at the semiconductor frequency boosting technologies. Typically, it's not that complicated as there's a clear starting point and then several iterations that improve on that technology. For AMD, that's not quite the case. Our story can either start in 2015 when AMD came up with the adaptive voltage frequency scaling technology, Or we can start in 2001 when ATI introduced the PowerPlay technology. While I would love to do a deep dive in PowerPlay going all the way back to 2001, I think for this video guide, maybe the best point to start off is in 2010 when AMD introduced their first AMD branded graphics card. In 2006, AMD acquired ADI Technology, a Canadian GPU semiconductor graphics company, for about $5.4 billion. The acquisition was part of AMD's plan to change how CPUs are built. In AMD's vision, the future of the CPU was not just a chip, but an SoC or system on a chip. The SoC would integrate functions like I/O and graphics alongside the CPU. In addition to developing a true system on chip, acquiring ATI Technology also brought AMD to the forefront of the discrete graphics market. AMD continued to market their discrete graphics under the ATI Technologies brand until the Radeon HD 5000 series launched in 2009. On October 22, 2010, AMD launched its very first AMD-branded discrete graphics card in the form of the AMD Radeon HD 6870. Less than 2 months later, AMD launched the new Terascale 3 GPU architecture and Northern Islands product family with AMD Radeon HD 6970 as the flagship product. Among the many novelties, AMD introduced a new dynamic voltage frequency scaling technology, DVFS, called AMD PowerTune as the successor to the acquired ATI PowerPlay technology. ATI introduced the PowerPlay technology in 2001 as a form of dynamic power management, or DPM, for their mobile graphics. In short, PowerPlay consisted of 3 fixed power states, each defined by a specific power, voltage, and frequency for the GPU. As the workload shifts from low to heavy and back, the power state adjusts accordingly. This ensures maximum performance when needed for heavy workloads and minimum power usage when there are no workloads at all. Traditionally, the power states have fixed voltage and frequency. However, workloads can vary significantly in how they use the GPU. As a result, GPU power draw in the highest performance state can differ wildly depending on the specific application. If we had an unlimited power budget, this would be no problem. But unfortunately, we're always power limited. Semiconductor companies like AMD address this challenge by utilizing a TDP or thermal design power limit. The TDP captures the maximum power a product can reliably operate at within the warranty period. The voltage and clock speeds selected for the highest power state are therefore limited by 1. The worst case scenario for peak power use, 2. The maximum voltage that fits within the power budget, and 3. The highest frequency that the GPU can run given that voltage. These 3 compounding worst case scenarios result in a very conservative configuration for maximum performance. Furthermore, very few real-world applications would ever meet those worst case scenarios. So the result is that in the real world, you lose a lot of potential performance. A 2010 white paper lays out the argument for the AMD PowerTune technology. PowerTune aims to deliver higher performance optimized to the GPU's power limits by dynamically adjusting the clock during runtime based on an internally calculated GPU power assessment. By dynamically managing the GPU clock frequency based on the GPU's proximity to the rated TDP, the technology enables higher clock speeds in the highest power state. So, the AMD PowerTune technology allows for dynamic frequency adjustment to fit within the TDP envelope, rather than restricting the GPU's frequency by a worst-case power expectation. Essentially, AMD employs several inferred power states with lower GPU frequencies between the highest P state and the intermediate P state. To make the inferred states as effective as possible, it's essential to have high granularity in terms of frequency. The result is substantially higher frequencies and resulting performance in typical workloads like gaming while staying within the power budget. Another feature that AMD added to its portfolio when it acquired ADI Technologies in 2005 was overdrive. Overdrive was a new feature that was added to the ATI Catalyst 3.8 software alongside the release of the ATI Radeon 9800 series graphics cards. Its function was pretty simple. If you enable overdrive, then the GPU frequency would increase from 412 MHz to 419 MHz if the GPU temperature is below 56 degrees Celsius. By the third iteration of the overdrive feature, ATI had enabled advanced performance tuning tools such as manual GPU and memory overclocking and even an automatic overclocking function. The overdrive feature would continue to live within the ATI Catalyst software suite with the same overclocking toolkit even after AMD's acquisition and the introduction of PowerTune technology in 2010. With the transition from PowerPlay to PowerTune, the overdrive overclocking knobs also received a minor overhaul. Whereas we used to have just two options to control the GPU clock and memory clock, from the Radeon HD 6000 series onwards, we have three settings: high performance GPU clock, high performance memory clock, and power control. The high performance GPU and memory clock represents the maximum clock frequencies the card is allowed to run at in the highest power state. This maximum frequency is still constrained by the power usage and may decrease if the current power exceeds the TDP. The power control knob allows us to adjust the maximum power usage in the highest performance state. The last topic we must tackle before moving forward is the VBIOS. The VBIOS is essentially the BIOS on the graphics card, and it contains all the information required to boot up your graphics card. The VBIOS often contains multiple modules which provides information about the graphics card or defines certain specifications. On AMD graphics cards, a specific module called PowerPlay Info contains all information related to the performance specification, such as the frequency and voltage for each DPM state, power and thermal limits, and fan speed configuration. We can find this module by extracting the VBIOS ROM. In the past, enthusiasts could edit the PowerPlay module and flash a VBIOS with custom settings to their graphics card. Nowadays, AMD digitally signs the VBIOS firmware. While it's still possible to extract the VBIOS and make modifications, without the ability to correctly digitally sign, the card will not boot up with a custom VBIOS. The graphics software has a PowerPlay driver component that reads the information from the VBIOS and configures the appropriate frequency, voltage, and fan speed configuration. End users could override the PowerPlay driver configuration using a soft PowerPlay registry entry. This registry entry is essentially a direct copy of the VBIOS module. We'll touch on this topic a couple of times as it's particularly relevant for overclocking. In January 2012, AMD launched the brand new Graphics Core Next GPU architecture and the Southern Islands product family with the AMD Radeon HD 7970 as the flagship product. 6 months later, on June 22, 2012, AMD introduced the AMD Radeon HD 7970 GHz Edition graphics card in response to the launch of the NVIDIA GeForce GTX 680. As the name already suggests, the GHz edition was a higher clock version of the same 7970 launched 6 months earlier, but with a twist. There's a boost. AMD PowerTune technology with Boost, or PT Boost, introduces a new approach to maximizing out-of-the-box frequency and performance. The idea is pretty simple. AMD adds a boost P state on top of the previous highest P state. This additional P state allows for extra voltage and thus higher operating frequency. The boost P state works the same as other P states, as the internal power usage estimate primarily drives it. However, on top of that, AMD also adds temperature into the equation. AMD calls this digital temperature estimation, or DTE. AMD estimates the actual junction temperature using DTE instead of assuming the GPU is operating at the worst case junction temperature. On March 22, 2013, AMD launched the second generation Graphics Core Next GPU architecture and the Sea Islands product family with the Radeon HD 7790 as initial flagship product and the Radeon R9 290X as the later flagship product. AMD also introduced an enhanced version of PowerTune technology alongside many new improvements. Until now, AMD's technology offered 4 distinct dynamic power management states: boost state, high state, intermediate state, and low state. Several inferred states had slightly lower frequency but identical voltage as the master P state between the boost state and the intermediate state. While this implementation offered AMD many improvements in performance per watt and power efficiency, a key drawback was that these inferred states didn't adjust the operating voltage. However, as we all know, voltage is a crucial driver for power usage. The enhanced version of PowerTune doubled the amount of DPM states from 4 to 8. That also effectively doubled the clock voltage pairings and, in theory, should offer more significant power efficiency gains. However, AMD did not continue with the inferred states, which reduced the clock frequency granularity. Implementing more fine-grained power states is not that straightforward. First, you need to switch as quickly as possible between states to optimize for power efficiency. Second, you also need fast and accurate telemetry to enable more rapid switching. The enhanced PowerTune technology relies on the AMD SVI2 interface. SVI stands for Serial VID Interface and is an AMD-designed VR controller interface. The second generation SVI was initially released in early 2010 and provides a range of features including greater granularity in voltage selection, faster data rate, and telemetry functions. As a result, the enhanced PowerTune architecture includes 3 main inputs: hardware temperature monitoring, internal power and current estimates, and external VRM telemetry inputs. The SMU evaluates these inputs and decides which is the optimal DPM state for the GPU. The DPM state then determines the clock frequency, the voltage, and the fan control setting. As the GPU will switch faster between states, it's also more challenging to know at what frequency the GPU is operating. To accurately communicate the actual operating frequency to the end user, AMD introduced the effective clock. The effective clock is essentially the average clock frequency over a period of 50 milliseconds. The final aspect of the enhanced PowerTune is exposing the ability to adjust the GPU target temperature. Before continuing with the AMD GPU frequency boost technology, let's make a small sidestep to the CPU side of things. In 2014, AMD launched their 25x20 initiative, which was a bold initiative to improve the power efficiency by 25x by the year 2020 in their mobile processors. They proudly announced having exceeded this target by achieving 31.7 times energy efficiency 6 years later. To incredibly oversimplify this challenge, there are 2 main ways how AMD got around doing this. 1. Increase the compute performance for a given power budget through architectural innovation of their CPUs and GPUs integrated into the APUs. 2. Decrease the power use for a given compute performance by innovations in real-time power management and silicon-level power optimizations. A first stepping stone in that direction was the introduction of voltage adaptive operation and adaptive voltage frequency scaling technologies in Carrizo. Carrizo is a 15-watt 28nm APU, part of the 3rd generation Bulldozer-based microarchitecture codenamed Steamroller. Importantly, it was the first AMD product to introduce AVFS for CPU and GPU cores. In a modern processor, everything starts with the power delivered from the 12-volt DC rail of the power supply across the motherboard to a voltage regulator. The voltage regulator then converts it to about 1 volt. That 1 volt is then delivered via the motherboard to the processor socket, where it gets transferred via the socket pins to the processor package and ultimately ends up at the processor die. The voltage to the processor is not constant. The processor uses higher voltage when it boosts to a higher frequency in response to a demanding workload. Conversely, the processor uses lower voltage when in an idle state. Switching from high to low load and vice versa causes significant voltage fluctuations. This phenomenon is commonly known as a voltage droop. The problem with voltage droops is very well known to overclockers. A voltage droop can cause the operating voltage to fall too low, causing system instability. In the past, chip designers would address this issue by supplying 10 to 15% excess voltage to ensure the chip always has sufficient voltage even after a significant voltage droop. Unfortunately, power scales proportionally to the square of voltage. That means for every 10% increase in voltage, you'll have a 21% increase in power consumption. Clearly, if you're trying to improve power efficiency by 25x, looking at the voltage and having a tight grip on the voltage is an important topic. Carrizo addresses this with two technologies: clock stretching and adaptive voltage frequency scaling. Clock stretching is something any Ryzen CPU overclocker already knows very well. To keep it short, a circuit on the processor tracks the operating voltage and compares the average voltage to the droops. If the actual voltage drops below the average, the processor briefly reduces the frequency accordingly. The system can respond in nanoseconds, which means typically the user would not notice the temporary reductions in clock frequency. If clock stretching is active for an extended period, you would see a significant decrease in performance. Adaptive voltage frequency scaling is a technology that implements many silicon speed capability sensors and voltage sensors in addition to the already present temperature and power sensors. Silicon speed capability means the maximum operating frequency of a chip. AVFS enables setting the optimal frequency for a given power or performance level across process, voltage, and temperature ranges. More importantly, this technology can maximize the performance for a golden sample as well as a total dud of a chip. In other words, your golden sample will be able to clock a little bit higher than your total dud of a chip. Does this sound familiar, Ryzen overclockers? Anyway, now that we understand the purpose of clock stretching and AVFS, let's return to the GPU side of AMD's business. While AMD first introduced the third generation GCN architecture with the Volcanic Islands product family in 2014, it still featured the same power-tuned technology from the previous graphics cards. In 2015, AMD introduced their next high-end GPU, codenamed Fiji, and the Radeon 9 Fury X graphics card as the flagship product. In terms of power management, the Fury X improved from the previous generation GPUs as it featured the voltage adaptive operation and adaptive voltage frequency scaling technologies first introduced in Carrizo. Towards the end of 2015, AMD worked on a new driver and software package. Retiring the Catalyst moniker, which had served AMD and First ATI since 2002, the new software launched on November 24, 2015, and it was called Radeon Software Crimson Edition. Fortunately for overclockers, overdrive was still present and all overclocking knobs were still available. The successor to AMD Fiji, Polaris, was announced at CES 2016. The GPU would eventually make it to market on June 29, 2016 with the Radeon RX 480 graphics card. It's a bit fuzzy on whether Polaris was the first or second generation GPU to integrate AMD's clock stretching and adaptive voltage frequency scaling technologies. As we just learned, Fiji seems to have been the first. However, in the Polaris white paper, we read Polaris is AMD's first GPU architecture to take advantage of the advanced power management and circuit design techniques that have been developed for CPUs at AMD. A significant change for overclockers was retiring the overdrive feature in the AMD software package. Instead, AMD offered Radeon MEM as the toolkit for people who want to tune the performance of their graphics card. Radeon MEM offers a wide range of overclocking tools, including performance per watt profiles, automatic overclocking, manual overclocking, graphics card monitoring, exporting and importing profiles, and power limit adjustments. Alongside this second generation Polaris, AMD launched their next GPU, Vega. AMD Vega is a 14nm GPU based on the 5th generation GCN architecture. The GPU would eventually make it to market on August 14, 2017 in the form of the Radeon RX Vega 64 graphics card. Naturally, it inherits the AVFS and adaptive clocking technology from Polaris, but also comes with a couple of other relevant improvements. Vega also included a more powerful integrated power management controller. The new microcontroller allows for implementing more complex power control algorithms and the addition of a floating point unit allowing for higher precision calculations, Vega also added a third clock domain for its Infinity Fabric SoC level interconnect alongside the graphics core and memory domains. The Infinity Fabric connects the graphics core to the other on-chip functions like multimedia, display, and I/O. The Vega 20 refresh consumer products and world's first 7nm GPU launched on February 7, 2019 with the Radeon 7 as the flagship product. Vega 20 is a simple die shrink of the original Vega GPU launched a year earlier. Thus, there are only minor architectural differences. However, a significant change would come to how AMD tackles the challenge of power management. As disclosed in a Linux patch note from Vega 20 onwards, the GPU will no longer use the traditional PowerPlay driver, but instead use a new software SMU framework. A key line in the patch notes indicates that the system management unit reads the PowerPlay parameters from the vBIOS and stores the information with the system management controller. The SMC controls all power management related functions, including DPM states, clock frequency, and voltage. While this new approach was not implemented for Vega 20, it would become implemented with the next generation of graphics cards, as will become clear in the next couple of minutes. AMD Navi is a 7nm GPU based on a new microarchitecture called RDNA and came to market on July 7, 2019 as the Radeon RX 5700 XT graphics card. It gets a little fuzzy on the specific power management technology used in the current Navi graphics cards. We only know that there's no power tune on the product specification pages. Furthermore, overclocking support embedded in the new driver software package is entirely different. We now have a voltage frequency curve instead of having frequency and voltage control over specific DPM states. The voltage frequency curve enables the configuration of two distinct points, the upper limit and the lower limit. Each point can be configured with a specific frequency and voltage within arbitrary limits. Aside from the voltage frequency curve, there is also an option to increase the memory frequency and the power limit slightly. In the 2020 release of the Radeon Software Adrenaline Edition, a more general performance tuning tab replaces the Radeon WattMan. Again, the same features are still available, however, they're rearranged in a more easy to digest format. The second generation of RDNA products and Navi 20 series GPUs launched on November 18, 2020 with the initial flagship Radeon RX 6800 XT graphics card. It's again not very easy to cover what's changed on the GPU frequency boosting technology, as there's little to no information available from AMD. We can only highlight the slight change in the performance tuning software interface. The voltage frequency curve was exchanged for two sliders, minimum and maximum GPU frequency. We'll use these settings to overclock our card manually. In our second overclocking strategy, we rely on the overclocking toolkit available in the AMD Adrenaline software to overclock our Radeon RX 6500 XT manually. As I pointed out earlier, the AMD Adrenaline software houses a couple of performing tuning knobs that we can use to overclock our graphics card. Specifically, we have access to GPU frequency and voltage, memory frequency and timings, fan configuration, and power configuration. While at first sight it may seem that AMD is offering us quite a bunch of overclocking tools, in reality we're extremely limited. In terms of GPU and memory frequency, there's no way to override the default limits and go beyond what AMD allows for. In terms of GPU voltage, we're already at the maximum setting by default, and again, there's no way to override the setting. There are only two options to select for memory timings: the default timings and the so-called fast timings. In terms of power, we're also limited by AMD's maximum allowed limit, and there's no way to go beyond this. In short, ironically, AMD overclocking is the exact opposite of adrenaline. It's boring. It's just a matter of maxing out all the sliders, and that's it, with the exception of one, minimum GPU frequency. To understand the importance of the minimum GPU frequency setting, let's have a closer look at the voltage frequency curve of this Radeon RX 6500 XT. Generating the exact default voltage frequency curve is a little bit difficult because AMD employs AVFS to dynamically adjust frequency and voltage to a given situation. In this case, we manually generate the VF curve by checking the VDDCR GFX GPU core voltage at a specific frequency. We run the GPU-Z render test in the background to ensure the GPU is in the highest power state. To map the voltage, we ensure the minimum and maximum GPU frequency delta is exactly 100 MHz, which is the minimum delta allowed. The final result is that the GPU AVFS algorithm will set a GPU frequency between the minimum and maximum specified frequency. We record the maximum frequency set within those guard bands and the maximum voltage. That generates the following voltage frequency curve. As you can see, the curve starts at 720 mV for the lowest frequencies and ends at 1196 mV for the highest frequencies. The highest voltage is applied from around 2750 MHz to the maximum configurable frequency of 2975 MHz. When comparing the voltage frequency curve using GPU-Z render test and FurMark as the workload, we can see minor differences in both voltage and frequency for a given test point. The standard minimum GPU frequency is 500 MHz. By increasing this value, we essentially prevent the GPU from using the bottom part of the voltage frequency curve. In some benchmarks, this helps improve performance. However, increasing the minimum GPU frequency is not without its own challenges. The minimum GPU frequency option is a very valuable tool if you're looking to maximize performance in very demanding workloads that don't push the GPU frequency to its limit. However, it's only useful if there's no limiter that is throttling the performance. And unfortunately, that is the case on the 6500 XT. Twice unfortunately, it's also difficult to spot. To demonstrate what's going on, I tracked the relative performance improvement in two benchmarks, FurMark 1080p and Geekbench 5 Vulkan. We also set the following parameters. Then we start with a minimum frequency of 500 MHz and gradually increase to the maximum of 2875 MHz. The resulting chart looks as follows. We can see that the Geekbench 5 Vulkan performance scales up to a minimum GPU frequency of 2875 MHz. With FurMark, however, the performance drops sharply if the minimum GPU frequency exceeds 2600 MHz. AMD's GPU frequency technologies, such as clock stretching, are fantastic, but while these technologies prevent the GPU from crashes and instabilities, it also makes it challenging to detect performance throttling. If we set the minimum GPU frequency to 2875 MHz, the FurMark benchmark keeps running and Hardware Info keeps reporting both the GPU clock and GPU effective clock as 2800 MHz plus. So as an end user, you have no idea the performance is worse unless you check with a benchmark. We use 2600 MHz as our minimum GPU frequency and max out the rest of the sliders for this overclocking strategy. Upon opening the AMD Adrenalin driver software, go to the Performance tab. Click on Tuning. Under Tuning Control, Manual Tuning, click Custom. Set GPU Tuning to Enabled. Set Advanced Control to Enabled. Set Min frequency to 2600 MHz. Set Max frequency to 2975 MHz. Set VRAM tuning to Enabled. Set memory timing to fast timing. Set advanced control to enabled. Set max frequency to 2400 MHz. Set power tuning to enabled. Set power limit to 15. Then click apply changes to confirm the overclocked settings. We reran the benchmarks and checked the performance increase compared to the default operation. While severely restricted by AMD, our manual overclock still results in a nice performance boost of up to plus 15.92% in Geekbench 5 Vulkan. When running FurMark GPU stress test, the average GPU clock is 2602 MHz with 1.014 volts, and the GPU memory clock is 2384 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 60.3 degrees Celsius and 76.5 degrees Celsius. The average TGP power is 92.009 watts. When running the GPU-Z render test, the maximum GPU clock is 2962 MHz with 1.195 volts. In our third overclocking strategy, we will use the AMD Adrenalin overclocking toolkit to both overclock and undervolt our Radeon RX 6500 XT. While this process may sound very straightforward, again, there's a twist. The voltage slider that's available in the Adrenalin software seems to need no explanation. Seems very straightforward, but it's not as straightforward as it may seem. Looking back at our manually charted voltage frequency curve, we see that the top end of the frequency uses 1196 mV, close to the 1200 mV we see in the software. So, our gut feeling says the value shown in the software represents the voltage allowed for the highest frequency. But that gut feeling would be wrong. The voltage shown in the software represents the maximum voltage, or Vmax, allowed for the GPU. Similarly, as we can see from the voltage frequency curve, there's a minimum voltage, or Vmin, at which the GPU is allowed to operate. Any requested voltage from the voltage controller by the GPU AVFS algorithm is constrained by the Vmin and Vmax guard bands. Reducing the Vmax value negatively offsets the entire voltage frequency curve by a certain amount. To demonstrate this behavior, I again charted the voltage frequency curve, but this time with 1150 mV Vmax. I want to focus your attention on four things. First, you can see that the minimum voltage of 720 mV at the lower end of the voltage frequency curve, up to 1500 MHz, is not affected by the negative voltage offset. That's because there is a lower limit for the GPU voltage of 720 mV. Second, we can see that the voltage for frequencies between 1500 and 1800 MHz is reduced by less than 50 mV because the lower voltage limit of 720 mV is enforced. Third, we can see that the voltage for frequencies between 1800 MHz and 2850 MHz is, as expected, negatively offset by 50 mV. Lastly, we find that the voltage for frequencies between 2850 MHz and 2975 MHz is reduced by less than 50 mV. Surprisingly, our highest frequency of 2975 MHz is still using 1200 mV, just like at stock. Interestingly, the actual highest voltage of this voltage frequency curve seems to be 1.25 volt. However, this is by default capped with AMD's rule of 1.2 volt Vmax. Let me demonstrate how this works by charting the voltage frequency curve with a voltage setting of 1125 mV. I want to focus your attention on two interesting phenomena. First, as I alluded to in the previous segment, the voltage for the highest frequency of 2975 MHz is now lower than the Vmax of 1200 mV. With a negative offset of 75 mV and a resulting voltage of 1170 mV, we can conclude that the original voltage frequency point for 2975 MHz is around 1250 mV. However, that voltage is by default capped at 1200 mV. Second, did you notice the gap in the voltage frequency curve? Due to the excessive negative voltage offset, GPU frequencies between 1800 and 2450 MHz are no longer stable. However, frequencies lower and higher are stable. How odd indeed. This behavior continues when further reducing the Vmax. For example, at 1100 mV, only the highest frequency point of 2975 MHz is stable. This gap in the voltage frequency curve that appears when using the undervolting tool is the key to squeezing the most amount of performance out of your 6500 XT. We can extract more performance from our GPU by combining the information we gathered in the previous overclocking strategy by using the minimum GPU frequency setting. The negative offset reduces the operating voltage for a given frequency, thus increasing the headroom for additional overclocking. However, be careful. As I already pointed out, Increasing the minimum frequency too high may cause the GPU performance to drop sharply in heavy workloads. My approach to GPU frequency tuning is as follows. First, open the Adrenaline software and set the minimum GPU frequency to the highest value that doesn't cause performance throttling. Then, keep the FurMark GPU stress test running and monitor the current FPS. Reduce the GPU voltage setting to negatively offset the voltage frequency curve until you see graphical errors on your screen. In that case, increase the frequency slightly until you see the performance drop off. Repeat steps 3 and 4 until you find the right balance between instability and performance throttling. Using this approach, we can further increase the minimum GPU frequency to 2675 MHz with an adjusted voltage of 1125 mV. Upon opening the AMD Adrenaline driver software, go to the Performance tab. Click on Tuning. Under Tuning Control, Manual Tuning, click Custom. Set GPU Tuning to Enabled. Set Advanced Control to Enabled. Set minimum frequency to 2675 MHz. Set maximum frequency to 2975 MHz. Set GPU voltage to 1125 mV. Set VRAM tuning to Enabled. Set memory timing to Fast timing. Set Advanced Control to Enabled. Set max frequency to 2400. Set power tuning to Enabled. Set power limit to 15. Then click Apply Changes to confirm the overclocked settings. We reran the benchmarks and checked the performance increase compared to the default operation. After tuning the voltage frequency curve, our improved manual overclock enabled us to improve the benchmark performance. While still severely restricted by AMD, we achieve a performance boost of up to plus 15.92% in Geekbench 5 Vulkan. When running FurMark GPU stress test, the average GPU clock is 2687 MHz with 1.004 volts, and the GPU memory clock is 2384 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 60.7 degrees Celsius and 84.3 degrees Celsius. The average TGP power is 92.009 watts. When running the GPU-Z render test, the maximum GPU clock is 2949 MHz with 1.165 volts. In our fourth overclocking strategy, we call upon the help of Elmor and his ElmorLabs EVC2SX device to work around some of the power and voltage limitations present on this Radeon RX 6500 XT graphics card. I will cover two distinct topics. One, why do we need and use hardware modifications? And how do we use the ElmorLabs EVC2SX for the hardware modifications? It's hard to determine where to start with the situation analysis. Literally every aspect of this card is restricted, and it's restricted well before we run out of any headroom. We can max out the frequency sliders for the GPU and memory frequency, we're at the upper limit for the GPU Vmax, and we still have plenty of thermal headroom despite maxing out the power limit as our GPU reaches only 60 degrees Celsius during FurMark. As I discussed earlier in this video, since Navi 10, AMD has discontinued using the PowerPlay driver and moved all GPU power management functions to the integrated SMU. Unfortunately, we know very little about how the AMD GPU SMU works in terms of power management. AMD has not been very forthcoming with technical details on that topic. However, we can make a reasonable assumption that the SMU will read the VBIOS information at boot, store it locally somewhere on the GPU, and use that information then for power management. If that is the case, there are essentially two ways that we could work around the overclocking limitations. One, modify the VBIOS with a different configuration, or two, communicate directly with the SMU to override the stored information. Unfortunately, neither are a real option. The VBIOS requires a valid digital signature that only AMD can provide. Software VBIOS flashing tools will simply reject a VBIOS that doesn't have a valid signature. Modifying a VBIOS and flashing it onto the graphics card with a physical ROM flasher still gets the VBIOS onto card, however, the card will simply not boot up. Communication with the SMU is very complicated, and unless AMD provides direct access, it's simply not possible. The last option I want to discuss is the so-called soft power play tables. As a reminder, the soft power play table is just a Windows registry key that mirrors the information of the vBIOS power play info module, which contains the power management configuration. While AMD had said they would discontinue the use of PowerPlay from Navi onwards, soft PowerPlay tables could still work around the overclocking limitations on Navi 10 graphics cards like the Radeon RX 5700 XT. The most user-friendly approach is using More Power tool, which enables users to customize the registry entry with their settings. Unfortunately, More Power tool doesn't work with the Radeon RX 6500 XT because the PowerPlay info module for Navi 24 has a slightly different structure than prior Navi cards. But there are more problems with the soft PowerPlay tables. Even if you extract the PowerPlay info module from the vBIOS and build your own registry key, it still doesn't work. Yes, you can get the PowerPlay table to work, and yes, you can extend the maximum overclocking limits as shown in the Adrenaline software, but they don't work. Setting a value higher than the maximum default limitations forces the GPU in some kind of fail-safe state. As a result, the GPU is reduced to 500 MHz. That happens not only when we try to go beyond the default GPU frequency limits, but also memory frequency limit and even the power limit. We can only guess why this behavior occurs, but our original theory holds up. The SMU reads the power management configuration information from the vBIOS at boot, stores it locally, and then uses that information for real-time power management. Any value that's requested through the driver that is higher than what's configured in the SMU results in a fail-safe state. So the result is that unless AMD provides us with performance tuning tools, there's nothing we can do. Well, almost nothing. Now that we understand the needs and the purpose of the hardware modification, let's get started. On this graphics card, I will do one hardware modification. This modification adds an I2C pin header on the graphics card PCB, allowing us to communicate with the onboard ON semiconductor NCP81022 digital voltage controllers. We can then connect the EVC2SX device to the I2C pins and easily control the behavior of the voltage controllers. I will focus only on the voltage controller providing the GPU voltage and SoC voltage. The other voltage controller offers the voltage for the memory controller and the memory. I focus exclusively on the GPU voltage controller because that's where I obtain the only tangible performance benefit. When we open the ON Semiconductor NCP81022 datasheet, we find much information about the voltage controller. Under the SVI2 interface register map, we can find more information on the various settings for this voltage controller. The most suitable options for us are the special purpose offset, which we can use to offset the GPU and SoC voltage, load line, which lets us adjust the voltage load line, and ADC disable. It's that last one that will give us the most benefit. ADC is short for analog to digital converter and does exactly what the name says. Translate analog electrical signals into digital signals, mainly for data processing purposes. In the NCP81022 diagram, the ADC sits between the SVI2 interface and the multiplexer. SVI stands for Serial Vid Interface and is AMD's standard for communication between the VRM controller and the CPU or GPU. A multiplexer or data selector is an electrical device that selects between several analog or digital input signals and forwards the selected input to a single output line. The GPU sends VID commands for the GPU voltage to the voltage controller via the SVI2 interface. The controller then uses a DAC or digital to analog converter to set the voltage. Via the multiplexer, 6 analog inputs feed back information to the GPU. The ADC first converts these analog signals to digital information, which is then stored in the controller registers. The GPU will then read those registers back via the SVI2 interface and adjust voltage requests accordingly. The reported information via the ADC includes sensed GPU and SoC voltage, maximum capable GPU and SoC current, and slew rate for GPU and SoC voltage. By disabling the ADC, we essentially force the voltage controller to stop updating those registers. In fact, the information available in those registers would be the last updated ones. If we disable ADC when the GPU is in idle, those values will be very low. Again, we don't know how the SMU interacts with the voltage controller, but as a practical result of disabling ADC, we can use a lot more power. Also, the maximum voltage is no longer limited to the Vmax of 1.2 volt. In firmware, the power draw on the 6-pin connector, measured with the ElmorLabs PMD, doubles from about 75 watt to 150 watt. Also, the maximum voltage increases from 1.2 volt to 1.26 volt. The ElmorLabs EVC2SX is the latest addition to the EVC2 product line. The ElmorLabs EVC2 enables digital or analog control using I2C, SM bus, or PM bus. The device also has UART and SPI functionality. It can be considered the foundation for the ElmorLabs ecosystem, as you can expand the functionality of some ElmorLabs products by connecting it to an EVC2. In this case, we're interested in the two I2C headers that provide digital voltage control. I'll try to keep the step-by-step explanation as practical as possible in this video. Step 1. Identify the voltage controllers you want to control with the EVC2SX. We did this in the previous segment. Step 2. Determine how the hardware modification will work. And we also did this in the previous segment. Step 3. Ensure the EVC2SX supports the I2C device. You can refer to the EVC2 beta software forum topic for a complete list of the supported I2C devices. If your device is not listed, you can leave a message in the forum or Discord. On the EVC2SX, each I2C header has 3 pins: SCL, SDA, and GND. That stands for serial clock, serial data, and ground. It's essential to connect the pins on the EVC2 to the correct pins on the graphics card. Connect the various pins to the relevant points on your graphics card. Since there are only 3 pins, it should be straightforward. If you're unsure, use a digital multimeter to locate the ground pin on both the graphics card and the EVC2 I2C header. The data pin is always in the middle, and the other pin is the clock. Step 6. Open the ElmorLabs EVC2 software for voltage monitoring and control. You can find the relevant controls under the I2C submenu items. First, click Find Devices. That will check if any supported devices are present on the I2C bus. In our case, it will find 2 NCP81022 voltage controllers. One controller manages the GPU and SoC voltage, and the other handles the memory controller and memory voltage. We select the top voltage controller in the menu and immediately enable the monitoring function. If the I2C is connected well, you should now see the charts update. Now you can check if this controller indeed manages the GPU voltage. You can see the loop 1 output voltage jumps between 0.01 volt and 0.719 volt. Then you can configure the voltage controller using the drop-down menus. In our case, we simply change ADC setting from yes to no. After applying the changes, you should now see the monitoring charts flatline. You can change other settings as well. Remember that the loop 1 options control the GPU voltage and loop 2 settings control the SoC voltage. Before we move on to the overclocking settings and the performance, I want to show you one more neat little trick. As I already said, with the ElmorLabs EVC2SX, we can also increase the GPU voltage using a voltage offset. Now, as it turns out, when you increase the GPU voltage, you also increase the GPU frequency. We can use this trick to get our 6500 XT graphics card all the way up to 3 GHz. With ADC disabled, our maximum voltage for the highest frequency is about 1.26 volt. As we increase the voltage offset with the EVC2, we can increase the effective voltage. The maximum reported frequency increases from 2973 MHz at 1.16 volt to 2996 MHz at 1.36 volt. By playing with the Undervolt option in the GPU driver and the voltage offset function of the voltage controller, we can increase the GPU voltage to 1.375 volt. With this voltage, we see a maximum GPU frequency of 3002 MHz reported in hardware info. I also ran 3DMark TimeSpy to check the performance, and as you can see, it is possible to run 3DMark near 3 GHz with the Radeon RX 6500 XT. Unfortunately, again, I cannot really give you a technical reason for why that happens. I suspect it's related to either the clock stretching circuit or the AVFS technology, which adjusts the frequency dynamically based on the voltage present. So maybe when you V-droop below and the frequency drop below, if you force the voltage higher, the frequency goes higher as well. But that's just pure speculation on my side, so please don't take my word for it. Upon opening the ElmorLabs EVC2 software, access the I2C1 section. Click Find Devices and ensure two NCP81022 controllers pop up. Access the NCP8102220 menu. Enable the monitoring function. Verify that the monitoring is indeed active. Set ADC update to no. Click Apply Changes, verifying that the monitoring output is no longer dynamic but a fixed value. Upon opening the AMD Adrenalin driver software, go to the Performance tab. Click on Tuning. Under Tuning Control, Manual Tuning, click Custom. Set GPU Tuning to Enabled. Set Advanced Control to Enabled. Set Minimum Frequency to 2875 MHz. Set Maximum Frequency to 2975 MHz. Set GPU voltage to 1100 mV. Set VRAM tuning to Enabled. Set memory timing to Fast timing. Set Advanced Control to Enabled. Set Max Frequency to 2400. Set Power Tuning to Enabled. Set Power Limit to 15. Then click Apply Changes to confirm the overclocked settings. We reran the benchmarks and checked the performance increase compared to the default operation. Working around some of the electrical limitations of the RX 6500 XT allows us to maintain a higher GPU boost frequency for longer. That results in significant performance improvements in workloads limited by the minimum GPU frequency or the maximum permitted power. We see a maximum performance uplift of plus 34% in Geekbench 5 Vulkan. When running FurMark GPU stress test, the average GPU clock is 2931 MHz with 1.27 volts, and the GPU memory clock is 2384 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 71.7 degrees Celsius and 104.1 degrees Celsius. The average TGP power is an estimated 160 watts. When running the GPU-Z render test, the maximum GPU clock is 2968 MHz with 1.27 volts. In our final overclocking strategy, we slap on a water block and see if we get any better performance with cooler temperatures. The mounting holes on this graphics card are very close to each other, 43 by 43 mm, so finding a fitting water block was not easy. I eventually settled for a Parami universal GPU block I found locally here in Taiwan. It was still a bit of a hack job to fit the water block, but eventually everything worked. We used the same settings as our previous overclocking strategy as, well, all the sliders were already maxed out anyway. We ran the benchmarks and checked the performance increase compared to the default operation. The main benefit of adding water cooling is the significantly improved temperatures. During a FurMark stress test, the GPU and GPU hotspot temperature decreased by 8.5 and 20 degrees Celsius respectively. Unfortunately, since AMD has imposed arbitrary clock limits, there's no way to improve the clock frequency further to achieve better performance. The only place where we can see any uplift from our previous overclocking strategy is in FurMark, where the card can sustain slightly higher clock frequencies due to lower temperatures. When running FurMark GPU stress test, the average GPU clock is 2948 MHz with 1.27 volts, and the GPU memory clock is 2384 MHz with 1.36 volts. The average GPU and GPU hotspot temperature is 63.2 degrees Celsius and 84.2 degrees Celsius. The average TGP power is an estimated 160 watts. When running the GPU-Z render test, the maximum GPU clock is 2967 MHz with 1.27 volts. Alright, let's wrap this up. as I said in the beginning of my video, the point of this project was to get back into AMD discrete graphics overclocking. I figured that the RX 6500 XT would be a great starting point, as it's the latest RDNA 2 architecture, it's a 6nm GPU, and well, it was affordable at the time. Unfortunately, I was quickly proven wrong. AMD is highly restrictive when it comes to custom performance tuning. While it might be easy to immediately jump to the conclusion that AMD must hate overclocking, right? I think it's important to highlight a couple of things. First and foremost, we must recognize the tremendous progress that AMD has made in terms of power efficiency. They've made some truly genius voltage frequency technologies that allows for maximum out-of-the-box performance. Unfortunately, all of those technologies integrated in the GPU also have the annoying side effect that overclocking becomes extremely restricted unless the vendor specifically enables those tools. On the CPU side of things, AMD has provided enthusiasts with both Precision Boost Overdrive as well as OC mode. Those two tools allow enthusiasts to customize their CPU or their silicon performance, not just in terms of, let's say, maximum performance through overclocking, but also maximum power efficiency to, for example, undervolting. On the GPU side of things, while these options are incredibly lacking, it almost seems like the AMD GPU team is going out of their way to lock down the performance on GPUs or the overclocking potential on GPUs. To me, that seems like more of a self-defeating move than anything else. Take, for example, this 6500 XT. Media and customers alike crucified this card due to the lacking performance, right? It did not meet the performance expectations from the market. Looking at the overclocking potential, I'd say that probably the story about the 6500 XT could have been about the great overclocking potential rather than focus so much on the performance out of the box, especially in a time where reasonably priced high-end GPUs were very hard to come by. It seems like a very low-hanging fruit effort to enable overclocking and win back the hearts and minds of enthusiasts and gamers alike. I understand why AMD would want to do this. I understand that they want to have people pay a certain price for the value that is offered in a certain product, like a graphics card. I do think that AMD is maybe overlooking the fact that value offered doesn't equate perceived value, right? You can have a certain amount of value offered in your product, whether it's performance or software or whatever, aesthetics. It doesn't mean that every customer will look at what you've offered and say, yeah, it's exactly the value. I perceive that value as the value that you've offered to me. Furthermore, adding these advanced performance tuning options allows your customers to create their own perceived value, right? So from the base perceived value that they have, they can tweak it and tune it for more performance or more power efficiency, and therefore look at your product with higher esteem, give it a better evaluation, right? I think that's something that AMD might want to think about. Anyway, that's all for this video. I want to thank my Patreon supporters for supporting my work. As per usual, if you have any questions, feel free to drop them in the comments section below. I will also put up a written version of this video on my blog if you want to look through the overclocked settings or have a closer look at the performance results. And that's it. Till the next time.